Today we will be talking about finding exponential functions from their graphs and transformations on exponential functions. Exponential functions are very helpful for modeling growth and decay in many real-life fields such as finances, life sciences, and forensics. Understanding how to transform exponential functions helps us to better understand how these functions behave and how to better apply them to the real-world scenarios. Here's an example problem that we will solve together to practice this principle. But before we do that, it's good to get an idea of what the graphs of some basic exponential functions look like. Here are the graphs for f of x equals 2 to the x, g of x equals 5 to the x, and h of x equals 10 to the x. Notice that with each of these, as x increases, y increases without bound, and that as x decreases, y gets very close to the x-axis but never touches it. Thus, exponential functions have horizontal asymptotes, but no vertical asymptotes. Another helpful thing to notice about these functions is that they all pass through the point 0, 1. Any positive exponential function that is not shifted to the left or right, or up or down, will pass through the point 0, 1, because any number raised to the power of 0 will equal 1. This is helpful to remember when trying to find how an exponential function has been shifted or transformed. When we go to find an exponential function based on its graph, a base graph or base function we can refer to would be f of x equals a to the x. No matter what our base a is, this function will have a horizontal asymptote of 0 and will pass through the point 0, 1. Now let's talk about reflections. This base function of f of x equals a to the x can be reflected across the x-axis or the y-axis. To reflect the graph across the x-axis, we need to make our y value negative by making a to the x negative, like this. Note that this is different than making a negative and then raising it to the power of x, like this. This is what we would not want to do. Let's also note that now, instead of passing through the point 0, 1, we're passing through the point 0, negative 1. If our graph is reflected across the y-axis, that means that the base of our exponent is less than 1, and that we are decaying instead of growing. So when we see a graph like this, we should consider making transformations to the function f of x equals 1 over a to the x. Note that this graph still passes through the point 0, 1. The next thing we need to consider is a horizontal or vertical shift on the graph. A vertical shift is created by adding or subtracting from a to the x. A good way to identify our vertical shift is by looking at the horizontal asymptote of the graph. Instead of a horizontal asymptote of 0, like our base function, this graph has a horizontal asymptote of 4. This tells us that we need to move the base graph up 4 units. To do this, we want to add 4 to our base function, like so. Now let's talk about horizontal shifts. A horizontal shift is created by adding or subtracting something from x in our exponent. To shift a graph to the right, we want to subtract how many units it needs to be shifted. To shift a graph to the left, we want to add how many units it needs to be shifted. For example, to shift our base graph to the right 3 units, like this graph does, we would want to subtract 3 from x in our exponent, and our function would become f of x equals a to the x minus 3. Once we have figured out any sort of reflection or shifting, we can solve for our base. To do this, we pick a known point from our graph to set up an equation that allows us to solve for our base a. We'll talk more about this and put everything together using this example problem. We basically want to turn our base graph into our example function using the transformations we have discussed before. As a reminder, our base function is f of x equals a to the x, and it has a graph that looks something like this, passing through the point 0, 1. The first thing that we can notice is that we need to reflect our graph over the x-axis. So let's make our function negative. This would look like f of x equals negative a to the x, it would have a graph something like this that passes through the point 0, -1. Next, we can look and see that our horizontal asymptote in our example problem is -2. So we need to subtract 2 from our negative a to the x. So we have f of x equals negative a to the x minus 2. This graph will look something like this. It will pass through the point 0, -3. And notice we just get that from shifting this 0, -1 down 2 units. Speaking of the point 0, -3, notice that we actually want to be passing through the point -1, -3. This tells us that we need a horizontal shift that moves our graph to the left 1 unit. We know that this means that we need to add 1 to x in our exponent. This makes our function f of x equals negative a to the x plus 1 minus 2. This graph is going to pass through the point -1, -3, have a horizontal asymptote of -2, and look something like this. Now we can solve for the base of our exponent. To do so, we'll pick another point on our graph. The problem has identified this point, 0, -5. So let's use this point. We're going to need to set up an equality that allows us to solve for a. Let's do that by plugging 0 in for x and setting that equal to -5. That will give us negative a to the 0 plus 1 minus 2 equals -5. Let's simplify our exponent. 0 plus 1 is 1, so that will give us negative a to the 1 minus 2 equals -5. A to the first power is just a, so we really have negative a minus 2 equals -5. Now we want to isolate a, so we can add 2 to each side of the equation and multiply each side of the equation by -1 so that we can make a positive. This means that the base of our exponent is 3. When we substitute this into our equation for a, we have found that the exponential function for the given graph is f of x equals -3 to the x plus 1 minus 2. And this is the answer to our problem. So to recap the process we talked about in this video, to find exponential functions based on a given graph, we need to identify the following transformations. Is there a reflection across the x-axis? Is there a reflection across the y-axis? Is there a vertical shift? Is there a horizontal shift? Once we've identified these transformations, we can solve for the base of our exponent algebraically, using a point on our graph. If you have other questions or you want to learn more about this, here are some resources that can help you to learn more about exponential functions